So, good morning in Italy and good afternoon in Taiwan. And today is my great pleasure to welcome Professor Annalisa Iuorio from Italy, from Naples. And she will share with us her recent work. I think there's a preprint of recent work on this topic, the impact of autotoxicity on vegetation dynamic and mathematical and ecological overview. So we are very curious about this topic. So let's welcome Professor Annalisa Iuorio.
Thank you. Thank you very much for the invitation, the introduction. It's a great pleasure for me to share my research with you today. As you said, yes, this is basically an overview of several projects that I have been working on during the last few years, and also up to some very, very recent ones that are still a work in progress. I'm going to show you actually also some plots where you can really see that it's still a work in progress, but we're advancing quickly, and I'm quite eager to share with interested people already. So that's why I included them in this presentation. And so as we were discussing a little bit before with Gia, the main sort of mathematical tool that you are going to see, or the main mathematical structures, I should say, that you are going to see are spatial patterns and traveling waves. In particular, I'm going to show you how this, let's say, novel biological factor, which is called autotoxicity, induces movement in patterns of vegetation. And from, let's say, the perspective of the tools that I'm going to use, it's mainly going to be in the area of dynamical systems, and in particular in the area of so-called geometric singular perturbation theory, which is the area that I worked on during my PhD, and that basically I haven't abandoned since then. And there's many people that have collaborated with me on these projects, many amazing people. I'm listing here some of them. So Paul Carter from the University of Irvine in California, Arjen Dolman and Fritz Wehrmann from the University of Leiden in the Netherlands, Francesco Giannino here from Naples, more from the ecological side, Gabriele Grifo from the University of Messina, and Cinzia Soresina from the University of Trento, both here in Italy. So let me start by giving you, if now I see that, okay, there is a bit of delay, but let me give you first an overview of what is this biological factor called autotoxicity. So basically, autotoxicity is a byproduct of decomposing biomass. When plants die, essentially, you have to imagine that they release some compounds in the soil, and these compounds are toxic for the species that produces them, but they can have also a beneficial effect on other species in the surroundings, depending on how close they are from the genetic viewpoint. It plays an important role in a wide range of applications. It's actually my collaborators from the Agricultural Sciences Department in Naples even founded a startup to produce pesticides, like organic pesticides, based on this theory. So it has, let's say, a wide range of applications, even, let's say, much more concrete than what we mathematicians look at. But of course, for the purpose of today's talk, I'm more going to focus on the effect that autotoxicity induces on this type of spatial patterns of vegetation. And we're going to see that mainly toxicity is able to either induce movement in patterns that would otherwise be considered as stable, or actually even is able to produce some spatial patterns in environment where water is not necessarily a limited resource, but I will go through it, let's say, step by step. So the first thing that I wanted to do to sort of give you a flavor of what is ahead of you for the next minutes is an overview of the kind of projects that I'm going to touch upon in this talk. And it's, let's say, some of the projects that I've been working on in the past few years. connecting or putting together the dynamics of biomass and toxicity. And I sort of divided this into two classes. One is the class of models on flat grounds. These are basically models 1 to 3 that you see in the upper part of the screen. And you see below all the papers that refer to the specific kind of work. I will put the references at the end of the talk as well. Anyway, and let's say on flat grounds, basically we considered both only the dynamics of biomass and toxicity, for example, in model 3, with a cross-diffusion model that is extremely recent and that I'm going to show a bit in more detail in a while. But also in, let's say, models 1 and 2, we included the dynamics of water as well. So you will see reaction diffusion equations describing the dynamics of biomass, water, and toxicity, both in the sort of most standard setting that we could think of. And this is from the very first model that I worked on for my master thesis back in 2014 now, so quite a few years ago, but also including a logistic term to make the model more ecologically accurate. And this is a paper that I've been working on together with Paul Carter and Arjen Dolman and Fritz Fehrmann in 2024. So I'm going to briefly touch upon them and give a few details more about the cross-diffusion model. Then comes the bottom part of the slide, where instead of considering a flat ground, a flat environment, we consider a sloped terrain. And we want to see if the impact of autotoxicity on these patterns that we have observed in the case of sloped ground, of sloped terrains, of flat terrains persists or changes when we consider a sloped terrain. And we do a similar thing. So in model 4, we only consider interactions between biomass and toxicity, but in models 5 and 6, we also include the dynamics of water. And in general, I should say now that this characteristic of, let's say, including or not including water mainly tries to sort of explain or model environments where water is a limited or not limited resource, because as we are going to see in a bit more detail, often vegetation patterns arise in arid environments. So environments where water is not a very abundant resource. And it's really the optimization of water that drives the spatial pattern. But there are also experimental observations that say that you can find different types of vegetation patterns also in environments where water is not a limited resource. And that's where we think toxicity could play a stronger role. But I'm going to guide you through some of them in more detail. The one extra thing that I should say on the slide is that basically for, let's say, 5 out of 6 of these, let's say, boxes that you see, I applied geometric singular perturbation theory to analyze the patterns that were observed to emerge via numerical simulations, via continuation, in using different types of software. So it's really the tool that I am, let's say, not only more familiar with, but that I also think is more powerful to analyze this type of patterns arising in this type of problems. And in order to also give you a bit more of a feeling of how powerful and useful GSPT is for this type of problems, I will basically give you more details in the construction of stable patterns and traveling pulses for the model 3, so the cross-diffusion model, where we have already a preprint, but the GSPT part is a work in progress. So that's the part where I'm going to show you some figures that are still very preliminary, but to give you an idea of how it works. And also I'm going to give a few more details on GSPT applied for traveling pulses in the context of model 5. So this model that we have recently analyzed and published in SciUp this year. Okay, so to do this, of course, I don't want to assume anything, so I will just make a very short recap on what is geometric singular perturbation theory, or GSPT as we're going to call it from now on. So GSPT is a very powerful tool in the area of dynamical systems that allows to analyze systems of ODEs where a small parameter epsilon appears that basically induces a scale separation. In the original context, the independent variable was thought of as time. So you talk about fast variables when you refer to the x variables in this case, and slow variables when you refer to the y variables in this case. Because as you can see from let's say the blue box on the left-hand side, the x variables evolve as 1 over epsilon compared to the y variables that evolve according to order 1. So that's what makes them fast and makes the y variables slow. You can basically equivalently rewrite this system by rescaling the independent variable and obtaining an equivalent formulation of this system on the so-called fast scale, which is the green box that you see on the right-hand side. And again, like, I have a couple of things to say at this point. First of all, that the color coding will be, let's say, very important and, let's say, kept throughout the talk, because that's what I've been taught during the PhD. Slow is blue, green is fast. If you have an extra scale, you have to come up with a different color, but that's a different story. I will tell you more later on. But it was also extremely helpful because GSPT is very, let's say, very visual, I would say. And the color coding really helps you disentangling the dynamics and really understanding what's going on with the system. So, and another thing that I point out is that I told you now that the independent variable in the original context was considered to be time, but actually, as we're going to apply GSPT to traveling waves, traveling pulses, in that case, our independent variable will be, and we'll get to that in detail later on, will be the traveling wave variable, the typical x minus c times t, where c is the speed. So in that context, slow will mean on a large, let's say, z scale, and fast will mean on a short z scale. So you can also think of it as a spatial scale separation, not necessarily as a time scale separation. Okay, what is the advantage of writing your system in these two different forms? The advantage is that when you consider the singular limit epsilon 0 in the slow and fast scale, you end up with two different simpler problems that are called respectively the reduced problem when you set epsilon 0 in the slow scale, and the layer problem when you set epsilon 0 in the fast scale. And if you patch the information from these two subproblems, you get a skeleton that you can call gamma 0 for your, let's say, singular orbit that is, again, a skeleton for the real orbit, that is the orbit that solves the real original problem where epsilon is positive but small. And the last thing I should mention here is that basically the reduced problem gives you the dynamics of the slow variables on a manifold that is defined by the first algebraic equation that is called the critical manifold. And in the layer problem, on the other hand, you have the dynamics of the fast variables on layers where y is constant. That's why the name, the layer problem. And you can already see at this stage that actually the critical manifold represents also a manifold of equilibria for the layer problem. And this is something that we are going to exploit later on when we are going to set up our dynamical systems framework to analyze the problems that we are going to study little by little. Okay, so as I said, I will distinguish these two subgroups of problems into the problems that have to deal with flat grounds and the problems that have to deal with sloped grounds. So we start from flat ground to give you also the, let's say, the first model that we came up with, as I said already, few years ago now. So that's why I called it the so-called original model, because it was the first time that we put together the dynamics of biomass, water, and toxicity. So what did we do back then? We considered a system of 3 reaction diffusion equations for these 3 variables: biomass B, water W, toxicity T. And it may look like more complicated than it is, but actually it's an extension of a very classical model in vegetation patterns that is called the Klaus-Meyer model, where you only considered biomass and water dynamics. So we included the interaction between biomass and toxicity in order to, let's say, take into account this effect that I mentioned before. So to be a bit more clear, I put the cartoon to the right. So we have, let's say, we assume that the toxicity has a negative impact on the species that is producing it. So you have, let me see if I can do anything about it. Maybe yes. Wait. The pointer is better. Okay, so if I consider the biomass equation, I am basically saying that the biomass is sensitive to toxicity via this term S times T times B with a negative sign, but the toxicity is also produced by the biomass because you have a positive income over there, which is equal to Q times S times T times B. So this is basically what you would retrieve in the model that we have summarized on the right-hand side. And the idea is that you may see different types of parameters, but the main parameters that play a role in the analysis that we do are this parameter S, so how sensitive the species is to toxicity, K, which represents the toxicity decay rate, so how fast toxicity is removed from the system, and P, which is the classical precipitation rate that is assumed to be constant. So in this type of arid environments, you consider just the mean annual rainfall rate. And what did we retrieve? We obtained that basically if you switch off toxicity, so if you assume that the species is not sensitive to toxicity for some reason, you basically decouple the first 2 equations from the third. So you have the evolution of B and W, which is completely independent from the evolution of toxicity. And for a specific parameter range, let's say sufficiently low rainfall, but not too low, and let's say any value for the other toxicity parameters, because it doesn't feel it anymore, the biomass, you retrieve, let's say in 2D, you may see this kind of spotted patterns of vegetation. And if you consider 1D transect, you would see these symmetric bumps. And you see them as a stable pattern for a long time. Nothing changes. Everything is fixed to this specific pattern. On the other hand, if you consider, if you turn on toxicity, you may see that these type of patterns start moving. So if you turn on toxicity, independently of the, let's say for different values of the toxicity decay rate, let me see, because I have a video, so I see it on my screen, but I don't think you are seeing it yet. And I tried.
Yes, I can see a video.
Okay, cool. Okay, then it's just my computer is a bit slower, but that's fine. Cool. Okay, so thank you. You may see that this spotted pattern that was stable when you didn't have toxicity or where you had this sensitivity to 0 starts moving. And you may actually see also the emergence of so-called double scale patterns where a macro pattern appears, for example, a labyrinth that is stable, but within this labyrinth, you see this type of still like half moon shapes that keep traveling. And this is only because of autotoxicity. So this is a type of behavior that you would normally not retrieve in classical biomass water models. And this, of course, made, let's say, both us and the ecologists quite happy, because, of course, back then, the only comparison that we could make was qualitative. But this, let's say, lack of symmetry and this type of movement induced by autotoxicity was, for us, much more interesting, of course, from the analytical perspective, because we didn't have a model that only produced stable patterns, but we had a model that could produce both stable patterns and traveling structures. And also from the ecological perspective, this was somehow closer to experimental observations. So this also was, I would say, considering the fact that it was my first real research project, is really got me excited, and it's actually what got me to think, okay, maybe I would like to keep doing this for quite some time, and brought me, I would say, here today with you. But then this was for my master thesis, so at some point we had to conclude. We published the paper, and but we thought, okay, actually, to construct these type of structures more rigorously, what do we do, or what are the techniques that we could use? This was a kind of question that I kept having in my mind for the years, let's say, during my PhD years. And I didn't know anything about GSPT, so I didn't know that this could be the key. But then when I found out how powerful it is, I thought, okay, this is actually something that, this is a problem where GSPT could really be applied in a perfect way. So that's what actually, luckily, got me to also meet Fritz Fehrmann, who was in Edinburgh at the time. And we started working together on this, and we realized that actually, if you, let's say, non-dimensionalize this model in a suitable way, you really end up with the sort of an extension of very classical models that have been analyzed in detail, also using GSPT, that are the union of a sort of Klaus-Meyer-Gray-Scott model plus an extra equation that is of ODE type, because I forgot to mention it before, but in this first model, we assume that toxicity does not diffuse. So we do not have an explicit diffusion term, Laplacian term for the toxicity equation. So the type of solutions that we could retrieve in via our one-dimensional numerical simulations were these type of traveling pulses. So in yellow, you see the traveling pulse for the vegetation, the non-dimensional version of the vegetation. In blue, the traveling pulse for the non-dimensional version of the water. And in green, the pulse for the non-dimensional version of the toxicity. And this pulse moves to the right of the screen. So you really have this type of scale separation induced by our small parameter epsilon here, is represented by the square root of the ratios of the diffusion coefficients for the biomass and the water, which is very often considered to be a small parameter in a vegetation patterns business, because biomass is assumed to diffuse, and I say quote unquote diffuse, much less than how water diffuses, let's say. So you really have this scale separation that allows you to apply GSPT, and you can basically reconstruct, again in one dimension, but for us this was, let's say, sufficient amount of information. You can reconstruct both traveling and stationary pulses by analyzing a, in this case, 5-dimensional ODE system in the traveling wave framework using GSPT. So to give you an idea of what this looks like in dynamical, like let's say in the dynamical systems construction, you should see the panel on the bottom right. You want to basically, when you want to have a pulse, this corresponds to a homoclinic orbit. So you start from the zero equilibrium for the biomass and you want to get back to it. And in doing so, you first follow a bit your critical manifold. So you first have your slow dynamics, and then you have the fast jump that represents the pulse itself before you get back to your equilibrium. So you again have your slow portion of the orbit. So this is the kind of idea that is behind this type of constructions, and we are going to see it in more detail now for these two type of projects. And it's again a very powerful tool because it doesn't just tell you the orbit exists, it really tells you also more or less what the orbit should look like. So you can also have a comparison with numerical simulations, for instance, really have a sort of nice matching between the information that you get analytically and numerically. From
I ask the question here? Hello?
Yeah.
Annalisa, can I ask a question here? Yes. I noticed that there's maybe constant D in the S equation, right? There's a capital D.
Yes, wait.
Yes. Is this also a small parameter, or is this also a separation of scales? Because you mentioned epsilon. Epsilon is a separation of scale between water and what? Biomass, right?
Yes. Mm-hmm.
How about the scale between, say, biomass and toxicity, or water and toxicity?
Okay, no, the scale separation is, let's say, so each of the variables has a part that evolves on a fast scale and a part that evolves on a slow scale. Mm-hmm. Hopefully in the sketch on the upper right, you see that both V and S have this type of peak. Actually, S is a little bit smaller, but has a peak exactly below the biomass because toxicity is produced by biomass. So it has to be, let's say, in the same location. And then a slow part away from it. And the water is just the reverse because plants take water to grow. So when you have a peak of biomass, you must have a minimum of water, and the other way around. So all variables have this type of double evolution on the slow scale and on the fast scale in some sense. So this is, I don't know if I answered your question.
So one epsilon is enough. You don't need two small parameters.
No. I mean, actually, you anticipate what I am going to say in the next slide because you don't need it, but you could have more than one small parameter. And this is what we actually got in the model with Paul, Arjen, and Fritz in this paper in 2024, when we included also logistic effects for the biomass growth. So we included in the dimensional version, well, still in the non-dimensional version of the model, we included an extra parameter that represents the inverse of the carry capacity. And in that case, the model is very complex, very rich. In some sense, including the carry capacity makes things a little bit simpler from the analytical viewpoint, but you also have this emergence of a second small parameter. And depending on the interplay of your two small parameters, you may have different types of traveling pulses emerging, also having this type of, let's say, peaks on the top with what we defined as super slow plateau in between. So the construction here is way more complex. I thought this was, let's say, not the best example to start with to give you an idea of how GSPT can be applied to construct these traveling pulses. But hopefully after the end of the talk, if you got a better idea and you want to, let's say, have more information about this, you can check the paper and find all the details, because it really is a nice example of where you don't just have one small parameter, but you have two, and you really need to take into account the possible combinations, let's say, between the two. The, let's say, last model in the area of the sloped, of the flat ground, let's say, macro area that I have defined in the beginning, is this very, very recent model that I constructed in collaboration with Francesco Giannino and Cinzia Soresina. And it's a cross-diffusion model that only takes into account the dynamics of biomass and toxicity. So our, let's say, research question here was actually, can we reproduce stable patterns like Turing patterns without explicitly having an equation for water? Like, can we say that actually there could be situations that have been observed in nature where water is not a limited resource, and yet you see some kind of pattern. So the key here was to really think, okay, maybe we don't need to change the reaction part. Maybe what needs to be done is change the diffusion part. But instead of doing it in a sort of, how to say, a posteriori way, so really just say, okay, let's see what happens if we do it. If we put a cross diffusion term instead of a normal diffusion term, we try to really derive it from a sort of mesoscopic scale. So I will go little by little through it. So first of all, in this model, we considered, differently from before, that toxicity can affect the biomass dynamics in three ways. It can inhibit its growth, it can increase its mortality, and it can, we said, reduce the propagation of the roots, which is, let's say, a sort of abstraction of the more ecological concept, but this is more or less what we mean. And that's why you see a minus term in the diffusion part when it comes to toxicity. So the idea was to really say, okay, if we include all these three effects at a sort of, let's say, mesoscopic scale, and we use fast reaction limits to derive this model from a scale where the roots are divided into two subclasses that we define as healthy roots and exposed roots. What do we obtain? So in principle, that's what I meant when I said we didn't put the cross diffusion term directly. We started from this, let's say, level, previous level, considering these two subpopulations for the roots biomass, and then applying fast reaction limits, we ended up with this specific cross diffusion model. And this was, of course, also very nice for us because we obtained finally a condition for Turing patterns to emerge. Also, when we turn off the other two effects for toxicity. So it's really the only ingredient that you need is cross diffusion. And we could also confirm this and investigate this further numerically, both in terms of direct simulations. This is what you see at the bottom on 1D and 2D, but also doing numerical continuation using the software PDE2PAF, so which is a very powerful tool to do bifurcation and continuation for PDE systems. And all of this, let's say, we didn't actually have to do a major, I don't know, parameter sweep to find the parameters that would do exactly what we wanted to do. This was really something that came up by using previous parameters from the literature and just playing around with the cross diffusion part. So it seems to be, let's say, a fairly robust feature of this type of model. And so just the last comment here, you see this type of periodic pattern with also this type of double peaks on the top, differently from before, because before those patterns where those pulses were traveling, this is a stable pattern. So it's a stable spatial configuration the system reaches after, let's say, a suitable amount of time numerically. And it corresponds in 2D to a sort of reinforced boundary of this type of spots that you see in the 2D simulations, basically. So the question was also, can we construct this type of periodic patterns using GSPT? Because they also seem to have scale separation. So to do this, you need to, again, first non-dimensionalize your system. So you, again, have the appearance of this small parameter epsilon, which is, again, linked to a ratio between diffusion coefficients. In this case, we did include the diffusion part for the toxicity. But again, since we considered before that the toxicity diffusion was so small that was basically negligible, we also have here that the ratio between the diffusion coefficient for the toxicity and the one for the biomass is very small, so plays the role of our parameter epsilon. And I'm going to give you, for this specific problem, an example of how we construct things from the GSPT perspective, because I think it's a nice way to start getting a flavor of how these kind of things work. So the first thing you do, in this case, we focus on stationary patterns, so we don't even have a C variable for the speed. We really just rewrite our cross-diffusion system as a system of first order ODEs. So therefore, you start from 2 PDEs, you get 4 ODEs. Actually, you get 5 because of the cross-diffusion term. So you get 4 ODEs plus a 5th algebraic equation that gives you, let's say, the coefficient of the cross-diffusion part, in a sense. And that allows you to suitably rewrite your ODE system as a system of really 4 ODEs with respect to 4 variables, P, S, T, and U. As you can see, this is a so-called too slow, too fast, because epsilon appears next to the T and U equations and doesn't appear in the P and S equation. This is in blue because it's written in the slow formulation. But again, as we've seen in the beginning, if we rescale the independent variable, we can obtain an equivalent formulation on the fast scale, where now epsilon appears on the right-hand side by introducing the so-called fast scale. So in this sense, we keep the notation slow and fast, even though we are not talking about time anymore. Okay, so we focus actually for our analysis on an even simpler version of the model, because as I've said before, we realized that to retrieve this type of staple patterns and numerically, you don't even need growth inhibition or extra mortality. So we set these two parameters to 0 to simplify our model, and we obtain an equivalent formulation that is the one that you see here on the slide. So how do we analyze this problem from the GSPT perspective? We do what I've said in the beginning on a, let's say, general scenario. We start analyzing the layer problem. We start analyzing the singular limit, starting from the layer problem. We would obtain, setting epsilon 0 in the fast scale, the system that you see on the upper right part of the slide. And P, in this case, is considered with a bar because it's constant for the layer problem. So it's one of these layers that I was mentioning before. And the critical manifold, as I've said, is the manifold of equilibria for the layer problem. So you can see it either in the TP space, so in 2D on the upper picture, or in PT, I think it's PTQ space on the lower part. It's composed of, it has this kind of S shape that is not really S because of the special form that we have for our function theta, but it's composed of 3 parts, 2 of which are attracting, the left and the right one, so the blue and the light blue. And the middle one that is unstable, but doesn't play a role in the construction of our periodic orbits, because our periodic orbits in, let's say, in the dynamical systems framework that we're looking at correspond to the orbits that you see in the 3D picture on the bottom. So they will be really the union of these 4 pieces, 2 blue, 2 green. The blue ones will be the slow parts that evolve on the critical manifold, and the green parts will be the jumps between the left and the right part of the critical manifold that correspond to the peak going up and the peak going down in our periodic orbit. So let's say I don't go too much into details, but basically what I want to say is that we end up having, let's say, a proposition that really tells us what is happening in the layer problem, where we have these sort of double heteroclinic connections, which are the double jumps that we need to construct our periodic orbit. Then we move to the reduced problem. So we set epsilon 0 on the slow scale, and we end up with the PS sub problem that we have over there on the critical manifold. Since we are on the critical manifold, it's more convenient to actually write this system in terms of T and S rather than P and S. But T and P are related because we are on the critical manifold. So we end up having both, let's say, the dynamics on the left part of the critical manifold and on the right part of the critical manifold. We can fully resolve them, determine the so-called takeoff and touchdown sets. So we know where the fast orbit is allowed to land and where it is allowed to leave. And this gives us the, let's say, precisely the points where the fast orbit should land. Then we are allowed to follow the slow flow until we are not allowed to leave again. And this is what finally gives us our periodic orbit as a singular solution. So the singular skeleton for our real solution in the, let's say, in TS space, it would look like this. So this is what I meant when I said you jump, you follow the slow flow on the critical manifold on the left-hand side, but then you're allowed to leave again. So pick another heteroclinic connection to go on the right part of the critical manifold, and then again follow the slow flow. And this gives you the full periodic orbit that corresponds to your to the periodic pattern that we've seen before. I think I will skip the details of the proof, but essentially, as soon as you have fixed one of the slow orbits on the left-hand side, there is only one way to close the loop. So you have really a family of periodic orbits parametrized by this value. So this is what gives you also your family of periodic orbits that are also observed numerically. Okay. On sloped ground, we have a slightly different scenario, because in that case, actually, what we see is that because of the slope, already models that don't take into account toxicity explicitly exhibit traveling solutions. And these traveling solutions are induced by the fact that when water falls from the sky by means of precipitation, and especially in arid environments, the soil is not so humid, so water doesn't infiltrate in the soil immediately. You have to imagine a sort of biological crust. What happens is that the water starts flowing downhill and infiltrates more easily whenever it finds vegetation. So as soon as it finds vegetation, it can penetrate in the soil. Biomass is then, let's say, more able to grow there. Whereas the, let's say, the part to the back of the vegetation gets less water, so dies out more quickly. And this is actually what creates, in time, these kind of traveling stripes that move uphill, in the uphill direction. So here, of course, we see only a cartoon of a one-dimensional perspective on the side of the slope, but this is actually the type of mechanism, ecological mechanism, that there is behind. And that's why, in this case, the movement is not induced by toxicity, it's just, let's say, intrinsic in the type of biological mechanisms that connect biomass with water. So for this type of class of models, we tried to first, let's say, still in environments where water is not a limited resource, we tried to connect, let's say, to create a model that was only taking into account biomass toxicity dynamics, but really try to capture, again, this type of movement. And we had in mind some very concrete scenarios that are taken from different locations here in Italy. And you see on the right-hand side some kind of aerial photographs where you have either this type of rings or this type of arcs that appear to be actually moving uphill. So in this case, we constructed fairly simple biomass toxicity model, where for the toxicity, we also included an advection term where the slope parameter is space dependent. And the idea And again, I'm going to try to show you a video. I don't know how successful that will be. The idea is to reproduce this type of patterns on real sloped profiles, because numerical simulations you can do on real sloped profiles. And so you can really see that if you simulate this model on real sloped profiles, you retrieve the type of patterns that you've seen before. So in this case, we started from a much simpler analysis, so only considering constant slope parameter, but this is, let's say, for future perspective to really consider an explicitly space-dependent parameter. And this is something where also the colleagues in the Netherlands have done much progress on in the last few years. So hopefully we can pick up this problem again and include this more explicitly. But even if you don't do it, you have this type of traveling wave solutions. You can see how toxicity influences, how tall the peak can be. You can infer the asymptotic speed of the pulse, and you can also play with, let's say, the different toxicity parameters to try to reproduce the different types of patterns that are observed experimentally. Okay, the fifth model is actually the one where I was talking about, let's say, the very recent paper that we published with Gabriele Griffo and Fritz Fehrmann. In that case, basically, we have, again, an explicit biomass water toxicity model. So water is included as well as toxicity in the model, but instead of a diffusion term for the water, we considered an advection term. And this is really what mimics this sloped terrains that I was mentioning before. So in a way, our goal was to try to see if we are on sloped terrains and the movement is already induced by water, what is the role played by toxicity in this business? And you see that already in a previous paper, it was shown that you can have different types of traveling pulses. So the Messina group has already investigated using weakly nonlinear analysis what happens at or close to the instability threshold. But also you see that numerically you have these very singular traveling pulses emerging, again divided into the three components. Let's say the non-dimensional version of the water is the upper left, the non-dimensional version of the vegetation is the upper right, and the non-dimensional version of toxicity is the lower left. So very singular in this case. And the extra complication here is due to the fact that, differently from the model that I've shown you before, it doesn't suffice to only have two scales. You need three scales. So in this case, besides the slow and fast scale, you also have a super slow scale that's why I said I will get back to the color coding eventually. We decided to use to let's say describe using the color purple. So purple for us will represent this super slow scale. Okay, so when you apply GSPT in this case, in some sense, is a little bit simpler than the model that I've shown you before, the cross-diffusion model. But in another sense, is a little bit more complicated because you have these three scales instead of two. So the first thing you do, you include a traveling wave framework. Now you're interested in traveling waves, so you really need to have also the speed in there. That transforms your reaction diffusion system into a system of 4 first-order ODEs. Then another very delicate passage that you very often need to do in order to make sure that you capture the type of solutions that you observe numerically is to rescale the variables. And you do this actually being informed by the numerics. So you let the numerics guide you also in order to find the right scaling for the variables that you see over here. So instead of epsilon now, you replace epsilon with a rescaled version of epsilon that is represented by this parameter delta. So now delta will be our single small parameter. So now we only have one, but it's delta, that is the rescaled version of epsilon. And you finally do this last step, which is replacing one of the variables with a combination of the other variables in the system. This also in a previous paper by 2018, in 2018 by Paul Carter and Ariane Dolman was done for a, let's say, similar system. And it's really to make the scale separation in the system clearer. So you end up with a system of 4 first-order ODEs of this form. And your traveling pulse, that is, again, in the dynamical systems framework, a homoclinic orbit, homoclinic to an equilibrium of the full system, will look like this in the singular limit. So the skeleton of our traveling pulse will look like this. Your equilibrium that you want to construct a orbit homoclinic to is located at W equal A, V equals 0, S equals 0. So it's the purple dot that you see over there, P1A. So you will first follow the super slow flow along the W axis until you pick one of the orbits of the slow flow and reach this point P3. Then 2 heteroclinic connections in the layer problem going through this point P2 will allow you to go back to your equilibrium located at P1A. And this will close your homoclinic orbit, and this will give you your traveling pulse. So to do this, again, in the singular limit, we analyze the 3 different scales now separately. We start from the layer problem. And again, as we've done before, we see that the critical manifold is a manifold of equilibria for the layer problem. It will be composed of, let's say, 3 pieces, M1, M2, M3, but actually the main pieces that will play a role in the construction are M1 and M3. Then in the slow scale, if we set delta 0 on the slow scale, we end up with the first reduced problem. This reduced problem gives us the dynamics on the critical manifolds, but again, basically the dynamics on M2 are biologically unfeasible because they would bring you to negative values of S, and S for us is a positive value, is the non-dimensional version of toxicity, so it cannot be negative. So you only look at the slow dynamics on M3, and this is what you have over there. To see the dynamics on M1, you need to go to the super slow scale. So you have the reduced problem on the super slow scale. That is extremely simple. You simply have this unstable equilibrium at W equal A that brings you away from it. And this is what starts the homoclinic connection. Okay, so basically the first result that we have at the singular level is that your homoclinic connection, your traveling pulse is given by the union of these 3 pieces. And the general strategy that you adopt to prove this is the following. You know that you have first this super slow transition, then a slow, then a fast. But you don't know a priori where you have to stop along M1 to pick one of these slow orbits on M3. A priori, you don't know. Just as a priori, you don't know what is the value of S star that will bring you precisely to this point P3 of A S star when W is equal to A. So the criteria that you adopt is you find these values that we call W star and S star, ensuring that there is a double heteroclinic connection that can close the loop between P3 of A S star and P1 of A. So to do this, this double heteroclinic connection is actually, in some sense, simple, because one part of the heteroclinic connection that lies entirely in the hyperplane S equals 0 was already studied by Paul and Ariane in this 2018 paper, because they did a similar analysis on a Klaus-Meyer type model. So when toxicity is absent, this is exactly what we retrieve. The second part of the orbit, the one going from P3 to P2, this is what actually gives us the value for S star, which has to be equal to A over D. And once you have S star, so once you know P3 of A S star, you only need to follow the slow flow backwards, and this will give you the value of W star, which in this case has to necessarily be 0. So that's why you see it pictured as you see it in the sketch really going through the origin, because this is what you get from the analysis. And actually, the last comment that I'm going to make here is that the speed is dictated by the first heteroclinic connection, so the one that Paul and Arian already analyzed. So in a way, the fact that at this stage we are including toxicity is not really affecting the speed of the traveling pulse itself. Okay, I will skip some of these other details to tell you that basically in this case, we can also prove persistence of the orbit when delta is positive but small. I haven't shown this in the cross-diffusion model because, as I said, that's already, let's say, that's still work in progress. So we have constructed a singular skeleton, but we haven't proved persistence yet. Here, this is a published work. We have already proved persistence. And again, I will skip the details for now. In case you want to have them during the question session, you can ask me. And the last thing that I wanted to show is the auto continuation that we performed. So we wanted to check, or let's say to corroborate our analytical findings with numerical continuation with respect to the different parameters in the system. And not only did we find that indeed the law that we get for the speed is quite accurate, but also that, let's say, the toxicity parameters indeed influence the structure of the pulse, but not the speed. And that when you consider h equals 0, h is this like non-dimensional version of the sensitivity parameter, you really get what Paul and Arian already got in this 2018 paper, but the techniques to get this type of traveling pulses are actually quite different because they need to apply blow-up in order to close their homoclinic connection because of the absence of toxicity, and we don't. So toxicity in this case adds an equation but simplifies the analysis in a sort of counterintuitive way, but that's what it is. And in phase space, this is the last check that we made. We do retrieve that the numerical solutions have the shape of the skeleton that we constructed analytically. So you can really see how the two approaches match nicely, or let's say how GSPT really is informative, not just about existence, but also about what to expect in terms of shape for your solutions. Okay. The sixth model, I don't have time to discuss it, but just wanted to tell you that what we are currently working on with Gabriele and Fritz is an extension of this model, including inertial effects. This basically brings you from a parabolic framework to a hyperbolic framework. It's more interesting from the mathematical viewpoint because it also allows us to sort of push GSPT beyond, let's say, the standard context of reaction diffusion systems, but also from the ecological viewpoint because inertial effects have proved to play an important role in vegetation dynamics since, let's say, the response of ecosystems is not instantaneous. So this is definitely something that should be taken into account. So we are going to keep working on that. Actually, this afternoon, we have a meeting precisely about this project. So let's say, I hope I have convinced you that, let's say, there is a lot of interesting things to do in this area, not just from the ecological viewpoint, making models more accurate, including biological effects that the applied people think are important, even though they make our models more complicated. They make our models more complicated, but this also allows us to push our techniques even further and really make even more beautiful math, in my opinion. I leave you with a list of references for basically all the works that I mentioned in this talk and maybe some more even. And I thank you very much for your attention.
Thank you, Anna, for giving us this very nice talk. I think indeed you have already provided 6 talks, okay? You have the 6 sessions, yes. Okay? Thank you very much. Yeah, so please, if audience, if you have any question, comment, remarks, just unmute your microphone and then ask. Yeah. So if not, maybe let me start with a question. Can you go back to your slides about modeling cross diffusion?
Yes.
Yes. I'm not sure whether my question is naive. So there are unknowns like RE, RH, right? Like before you tackle the phase limit, phase diffusion limit or phase limit.
Yes.
Yeah, this one. Yeah, yeah. Okay. Suppose now I don't know this closed diffusion model. I have this three equations. So what do I need to solve? I need to solve 6 ODEs, right? If I apply singular perturbation setting. Then what's the advantage of taking this phase limit, phase duration limit? This is my first question. Because my naive idea is I can just study this duration diffusion system about RH, RE, and T.
Right.
What's the
So
main advantage?
yeah, so basically the idea is the following, and I should say Cinzia is the expert on this, but I hope she would agree with what I'm about to say. So basically this division between the two subpopulations of roots biomass, healthy and exposed, this is something that you do at, let's say, a quote-unquote mesoscopic scale, because the term is not precise, but it's not really micro scale, so it's something in between in a way. And you, at this stage, in the equations for the healthy and the exposed roots, you are only including the fact that the healthy roots, let's say, have their reaction part, have their diffusion part, but have this this term that even, let's say, that has this prefactor of 1 over epsilon with these transition functions P and Q. I didn't have the space or the time to detail this a bit more, but these transition functions tell you regulate how healthy roots can become exposed, and in turn how exposed roots can get back being healthy. And this happens when they meet toxicity, in a sense. So when they meet toxicity, they become, from healthy, they become exposed, and after a while, or let's say when there is no toxicity in the surroundings, after a while they get back to being healthy. And you have to think that this type of strategy, let's say, was first introduced in the context of population dynamics between, let's say, prey and predators. So to really mimic the fact that actually in that case, preys are entering a sort of excited or scared state when they are around predators. So they move actually faster. Whereas if there are no predators in the surroundings, they move slower. So they are, let's say, they get back to a sort of quiet state. So this is a sort of slightly maybe more complicated to grasp distinction in the context of vegetation, but this is the idea behind. And the point is, here you would have these like 2 PDEs for the healthy and the exposed roots, and a third PDE for the toxicity. And this, let's say, in some sense, is a more complex model than it needs to be, because when you consider the fast reaction limit, you end up with a system of only 2 PDEs, but with this cross diffusion term. And
cross diffusion form is very difficult.
Indeed, but as you see, I think this is another example where I realized that, for example, GSPT applies to cross diffusion systems. It is very rare, but as you've seen, like once you see this in terms of GSPT, even cross diffusion becomes a sort of algebraic constraint that you have to incorporate in your ODE system. Of course, this makes it a little bit more complicated, but it's still a system of 4 first-order ODEs.
I see.
And I've seen worse systems. Like, I think I also had this attitude when I saw it the first time. I thought, oh, okay, with cross diffusion, what can we do? But actually, when you see it from the GSPT perspective, even the cross diffusion term just becomes some kind of algebraic constraint that you can
so friendly. This is so surprising.
So
so surprising.
At the end of the day, it's more innocent than it looks, I would say.
Yes. So in your opinion, if in the future, when there's someone who encounter this reaction diffusion system with a fast reaction, like at 1/epsilon, then your advice would be, let's take this limit and then derive some closed diffusion model.
I would say, at least for my experience, I can recommend it. Like if this fast reaction limit can be applied, yes, I think it's better to have a system of 2 equations, even when you have cross diffusion, than to have 3 PDEs.
This is really new to me, because this the original reaction diffusion system, essentially you have to solve 6 equations, but now you only need to solve, after this taking limit, you need to only solve 4 equations plus 1 algebraic relation. And
exactly.
Mathematically, this is a really, really big reduction. Yeah, this is something I've learned from you. Amazing. But
I'm happy to hear that.
But somehow, do you really lose any information after this reduction, or you don't lose anything?
No, because I mean, you study your system in phase space, so you have all these like P, Q, T, U variables. In the end, at the end of the day, you are interested in R and T, basically. But you can always go back, like, because of the relation that you have. Maybe I find it. Wait, maybe I go back there. Yeah. Let's say, because of the relation that you have between R, P, and T, that is represented by your algebraic constraint at the end, you can always go back. So in principle, all the information that you gain, let's say from the dynamical systems perspective, you can always trace back to your original system.
Sorry. I should have reformulated my question as follows. You say you rigorously derive this this closed diffusion model. What do you mean by rigorous? Rigor. What do you mean by rigor? I ask you this question because, when people want to approximate like a reaction diffusion system by some simple equation like Ginsburg-Landau equation, say near the onset of Hall bifurcation, they always need to rely on something like a center manifold theory, or some kind of like a renormalization technique. But I know this question is purely mathematical, but what do you mean by rigor here?
In this case, and again, Cinzia would be the expert on this because she is the one that took care of this derivation. To my understanding, in let's say, you really, I mean, this should be something, let's say, fairly standard in this fast reaction limit business. I am afraid I cannot provide you with more detail. Now I would need to relook again at what we wrote in the paper about this. But yeah, I think it's, let's say, from what I recall, let's say there weren't any I don't know, specific reductions that had to be applied, in order to go from this sort of mesoscopic scale to. But that's why I said, like, I know that, let's say, this I've experienced when she has given a talk about this project in context where there were people that work more in this kind of business, so in really deriving models from the microscopic scale and mean field limits. I think there is there are some differences. So I'm sorry that I cannot give you more details.
No problem.
But,
I mean, this is a win-win condition, right? If you have a reference, then I am happy. If you don't have a reference, then in the future you can have another paper.
Indeed. I like this approach.
No, I know this is this may be trivial or non-trivial, highly non-trivial. Okay, but I would say this kind of reduction is really new to me. Maybe I know I am just 5, but interesting. Yes.
I'm happy to do
Okay,
that.
so let me ask the audience. So, are there any other question, comments?
Yeah, thank
Please.
you for the talk.
Snow one, please.
Yeah, thank
Yes.
you for the nice talk. I don't know if you can hear me well.
Yes, we can hear you very clearly.
Yeah, I really enjoyed it. I got a couple questions. I don't know how much time left right now.
Unlimited.
Oh, unlimited. That's really nice.
No. Depending on Professor Annalisa's tight schedule. But
yeah,
it's fine. It's fine.
For the
Go
couple
ahead. Go ahead.
questions. And most of the model you mentioned they're PDEs. So I guess I'm curious, what kind of boundary condition or like superimpose over there, and how the boundary condition like basically influence your result. And second question is, so right here on page 9, so here there basically there's no water component, right? Just like biomass and toxicity. But cross diffusion looks like this is sufficient to produce turning instability pattern, right? So
yes,
I guess I'm curious. So what's the role and the water is playing really here and over here, and so water is neglected basically here. So and I'm wondering what water is doing because we're neglecting that part. And last question is, you mentioned about the slope toward the end of your presentation, right? So, and is that part of the advection?
Yes.
And could you comment a little bit more on that? Thank you.
Okay, thank you.
Okay.
So 3 questions. The first one is maybe one by one. The first question is about
I will go one by one. Allora,
yes.
The first question was about boundary conditions. In most of the problems that I've shown you, I was interested in, even in the ones that were on flat ground, except for the cross diffusion project. So this one that we see here on the slides. Basically, in all the other contexts, I was interested in constructing and analyzing traveling pulses. That's the bottom line. So traveling pulses in analytical context would require an infinite domain, which is something that we cannot reproduce in the numerics, of course, and I will not deny the fact that, especially when simulating these very singular models, the numerics are not trivial, because you have maybe peaks that are so narrow compared to the size of your domain, because you need to make it, let's say, quite large. So also, let's say, tuning the numerics is, let's say, not the most trivial business. The boundary conditions that we adopted in most cases are periodic boundary conditions, and this is to sort of try to reproduce this kind of, or mimic this kind of infinite domain that we cannot have numerically. For the patterns, like for the let's say Turing patterns here in the cross diffusion model, and also in the 2014 model, I think we also tried Neumann boundary conditions. But I would say for the patterns, they don't really, I mean, in general, they didn't seem to play a big role in the kind of outcome that you had. So this is the type of conditions that we've used, but I would say the numerics was always more delicate to deal with when we were trying to really see this kind of traveling pulse moving.
Right.
So this is the first one. The second one, what is the role of water in this cross diffusion model? Since we are neglecting it, I would say basically the idea behind this this project was that okay, if we see some kind of patterns in nature that are also in environments where water is not a limited resource, can it be that what drives these patterns is something else and not the fact that they have to optimize water? So by implicitly including the water in this model, we are implicitly saying that plants don't have problems in uptaking water. So basically, their growth rate, let's say, is always, let's say, sufficient, and let's say the resources that they have at their disposal are always sufficient. They are not trying to optimize them because they're scarce. So in principle, if you wouldn't have toxicity, the biomass would grow. You have a logistic term there, so you have, of course, a carry capacity. But that's, again, something to make the model more accurate from the ecological perspective. But in principle, let's say, also because it's also true that even when you have infinite water, the plants don't grow exponentially. Like it's not really like that. So, but if you wouldn't have toxicity, plants would grow and they wouldn't have any problem with their resources. It's really the toxicity that creates this kind of spatial heterogeneity and really leads then the formation of some kind of spatial structure. This is what we are implicitly meaning by that. And now the third question, the slope. The slope at the advection. So let me go to the corresponding slide. For example, I don't know, I think I can take this one. So here, for example, this is basically the last model that I've shown in a bit more detail. We have, and this again in a non-dimensional form, you have something quite similar to what I've shown you before. So the, let's say, the original Klaus-Meyer-Gray-Scott plus ODE model in non-dimensional form. The only difference here is that in the equation for the non-dimensional version of the water, so for U, instead of having a Laplacian term also multiplied by epsilon, you have this advection term. And the advection term is really because of the slope, you only have, or at least you have movement in a preferential direction that should really give you the fact that water is flowing downhill because of the kind of cartoon that I've shown before. So this is the kind of picture that you should have in mind. So it doesn't distribute evenly across the ground, the flat ground, but you really have that because of also the presence of these kind of biological crusts in environments that are more arid, water is flowing downhill, and then it activates this kind of mechanism that I was mentioning before, that it infiltrates more when it finds the biomass. But this is like the forefront of your traveling stripe or your traveling pulse, if you would see it in 1D. So you have this peak of biomass at the front, and then it dies out at the back because the front takes all the water and doesn't leave anything for the back. And if you see this, let's say, dynamically in time, this gives you the impression, let's say, of having a stripe moving uphill. So this is the mathematical sort of translation for this type of mechanism.
Cool, thank you. So basically, right now the spatial is a 1D, right?
Yes.
So suppose from 0 to something, whatever the length you're considering, right? So the left and is the downward, and so the flow, the water flow is go to 0, right? Or the beginning. Is that right?
Yes, exactly. Yes.
Thank you. So that's why I see. Thank you. Very, very, very helpful. Super cool.
Thank you.
Well, so any other question, comments, remarks? I have another one. Can you go back to a slide about 3 small parameters like delta tau or delta tau square? I remember this one.
Wait, the three scales.
That is super slow. Yeah, slow, fast, super slow. Yeah.
Okay. I think it's this one. Let me.
This one. No. That one. Yeah, this one. Maybe my question is a little bit too technical, but here you have 3 scales, but indeed, essentially, you have only one limit. You just take only one limit, which is delta.
Yes.
Because these these three scales are connected by the common delta, and I'm wondering what's the main difference if I take three independent scales? Let me call tau 1, tau 2, tau 3, and they are not related. And then I consider singular perturbation setting on these three independent scales. I know this may be, so mathematically, this may be more difficult, but I wonder, because maybe in real world, maybe these three scales, they are not related, right? This is a possibility. But I just want to see in your experience, if I consider this more complicated setting, what would happen? Or maybe it's sufficient to consider your setting. Your setting can already capture dynamic of three independent scales. This is my question.
Okay, it's a very interesting question. So I would say, in my experience, I haven't encountered such a scenario, but I think it's because, well, first of all, because if you want to hope to apply any of these techniques, you need your small parameter or your small parameters to be the one that sort of links the different scales. Maybe one example that I can think of is this example that I've shown at the beginning, where you had two small parameters. And so, of course, for each small parameter, you had a corresponding slow and fast scale. So the slow scale for one parameter is another scale compared to the slow scale for the other parameter. But you can always sort of say, or sort of order them in terms of which one is the slowest and which one is the fastest. So you may not have scales that all depend on one parameter, but you need to have some kind of scaling between the parameters that allow you to tell all the scales, like in which order they are. Otherwise, I think it becomes pretty hard to connect what you have in each scales to have this kind of singular skeleton. I would say this is my impression. I don't know if this answers your question.
Yes, I think it's possible that you can distinguish the scales by, for example, if tau 1 is smaller than tau 2, then you can say if tau 2 goes to 0, then tau 1 also goes to 0.
Yeah, exactly. So you still need an order. I don't think you can hope to patch the information that comes from the different scales if you don't have a clear idea of how these scales are related, at least in terms of slow fast.
I see. Somehow I have a conjecture, which is maybe naive. My conjecture is no matter how many independent scales you have, in the end, you can reduce this problem to your setting. If this is true, then of course you already justify your setting, already explain all possibility of choosing scales. If this is true, okay.
But in my experience, is also true that, I mean, even this is non-trivial in the sense that, as you've seen, there could be problems where you have two scales but two small parameters. There could be problems where you have one small parameter but three scales or maybe more. So it's also an approach that I think is, again, very powerful but very much problem dependent. So it's you really, that's actually also why I mentioned before, like the numerics kind of guides you in understanding what you are really looking for. Because sometimes we see also with continuation that maybe these models support different types of solutions with different types of features. Yes, so at some point you have to say, okay, what is the kind of solution that I want to construct? And if I want to construct that solution, what are the ingredients that I need? So what are the features that the variables need to satisfy? And this really guides you in the analysis. Otherwise, it's sometimes, I mean, there is not just one right path to take. So also to find the way to make things as close to what you want to construct as possible, and also as easy for you as possible, in the sense of extractable for you as possible, is, I would say, part of the game, a big part of the game.